A recurrence relation describes a sequence by a formula that gives the next value in terms of an earlier value or values. Recurrence relations are generally easy to find, but they're hard to use since in general finding the kth term requires finding all preceding terms. What we want is a closed form expression for the terms of the recurrence sequence, a simple formula that allows us to compute the kth term directly. To find the closed form, we need the recurrence relation, the starting value or values, and insight and creativity. A common strategy is to use an ansatz. That's an assumption on the form of the solution. The ansatz is justified because it works if it works. For example, let's try to find a closed form expression for the recurrence relation we'll assume that Sn is some type of function. So let's assume that Sn is, how about linear? So suppose Sn is some linear function. Now, we note that our recurrence relation tells us that the difference between Sn and Sn minus 1 is going to be n minus 1. And this must be true for all values of n. So if Sn is a linear function, then Sn minus 1 is, and I can look at that difference, which will be, but since this has to be true for all values of n, our ansatz doesn't give us a solution. And so we should try a different ansatz. So let's assume that Sn is some polynomial function of degree k. Then Sn will be, Sn minus 1 will be, and the difference will be. So it's still true that the difference should be a linear function. But notice that n squared minus n minus 1 squared is 2n minus 1. So if a2 is non-zero, the difference could be a linear function. But suppose a3, our cubic coefficient, is non-zero. Then the difference would include the difference of cubes, which would introduce a quadratic term into our expression. So we'll want a3 to be 0. Strictly speaking, this isn't a proof, but again, it will be justified later by the fact that it works. This suggests that if Sn is a polynomial, it has degree 2 or less, so we'll revise our ansatz and assume that Sn is a quadratic polynomial. Then Sn will be, and Sn minus 1 will be, so the difference will be, so first, we'll talk about how we should solve this. Expanding the right-hand side and rewriting it as a polynomial gives us, and in order for the two to be equal for all values of n, the coefficients have to be the same. So comparing the coefficients, our linear coefficient on the left is 1, and on the right it's 2a2. Our constant on the left is minus 1, and on the right it's a1 minus a2. And so solving we get now we still need to find our constant term. To find a0, we note that s2 is equal to 1. So if Sn is given by a quadratic expression, then the fact that s2 equals 1 tells us which gives us our form for Sn. Now that's how we should solve this, but how we often solve this is something like the following. Since this relationship must be true for all values of n, it will be true for any value we choose. The form suggests we might want to use n equals 1/2, which gives us to get a2, we use the fact that we know a1 and choose another value for n, say n equals 1, which gives us, and again, A0 can be found in the same way. And remember, no computer was ever fired for making a mistake. We claim the recurrence relation with S2 equals 1 has closed form expression. This is an ordered, infinite sequence of claims, so we'll use induction. The base case. Note that we start with n equals 2, S2 equals 1, and we find, so the statement is true for n equals 1. Now for the induction step, we want to prove that if sk equals 1/2 k squared minus 1/2 k, then sk plus 1 equals, and we somehow want to get from here to there. So we do know that our recurrence relation tells us that sk plus 1 is k plus sk. And we can do some algebra. And, well, remember, algebra is a road that goes in both directions. So if we take a look at our destination, we can do a little algebra. Which takes us to our starting point. Now, remember, the last line you write is what you've proven. So we actually want to work our way backwards from our final line, back a step, back a step, and we know that that joins up the road, and so now this proves the induction step.